so I'm recording now. What I'm going to quickly do is bring you back up to speed with this. I do want to fix this and then we can move on, but I just want to show you what was going wrong, because if you were there yesterday, you'll know that everything I did, it just didn't work. So what I want to do is just open up that assembly and just explain to anybody who wasn't here exactly what was going wrong, because it was quite a bit, as you all should be well aware. So I'll close this and I'll just bring this onto the screen. So that was the assembly, and yesterday it was it was Ted Theodore Logan, and he spotted that this thing is far from symmetrically drawn. So I had a look at it and had a good look at it. This was a model I just ripped straight from GrabCAD. It was just a nice example of what I wanted to do. And I looked, and the only thing that is actually drawn with some precision, well, only thing that's actually drawn, I don't want to put in precision because even that's poorly a bad example, is the lower arm. This actually does have dimensions to it, and I say even this is not so good, because let's just zoom into the thicknesses between each point. It is literally all over the place. Now, I wasn't happy with just saying that the model is crap, therefore we're not going to complete it. What I wanted to do is still find a solution for this, and there is a solution. I just totally forgot that this could be a possible solution for it. Right, you've got to follow me you've got to follow with me on this. So, as a reminder, if I run this, just to remind you all of the embarrassments. Oh, right. So if I come back. Right, that's appeared because, like an idiot, I've forgotten to delete all of my addressing. So I'm going to remove all the addressing. F5 that, yes. And the beauty is it's not a massively complicated model, so it's not like I'm going to be sat here forever deleting stuff. And then we apply again, F5. Okay, so zooming in. And that's his models. So if I run this again, let me just run this again. So that is where we finished up. We finished up in a good equivalent example of this. And it was well misaligned. Really frustrating, as some of you will have well noticed that it was very frustrating. So what I'm going to do is get rid of that for one. Now, this is literally saying in the axis, this cannot move like this, like this, like this. Now what I've found, it's actually mainly coming around the hub. The hub and the upper arm, these two are so poorly drawn that it's unreal. So what I decided to do is I put in an element that would allow me to have a bit of flexibility. Basically, imagine that if I come back onto here, imagine that this is on a shaft. And if it's on a shaft, it can just move slightly to the left or right. So what I can do is align one spot and get this to align to it. And this is purely because it's been drawn so poorly, to be fair. So the one way of being able to do this is, now we've seen this before, and it's frustrating that I just didn't think of this sooner. But you know when you get on a spot and you think, I don't know what's going on, it's bugging the hell out of me. So if I go down to multi-body, and I'm going to go to joints. If I use, that's just your revolute, but if I'm thinking of that joint sitting on a shaft, I'm actually going to use cylindrical. What this will allow it to do is it will allow it to just, one second, got a visitor. So Boris has arrived. So what this will allow it to do is this will allow it to just move out of that misalignment that's been actually modelled into it. So if I select the upper arm and this point here, I'm not actually going to change much. Now we set these axes so this thing would rotate in the correct area. So we'd already set this. So if I bring this in, lock that into position there and there, I'm just going to put that there and I'm going to comment that out like that. Now if I run it again, What it actually does now is it gives me that, which is rocking. So what it's done is it's now given that misalignment, but locked all the rotational, the revolute joints into place. So everything else is now happy to move, but the hub is now aligning itself with everything else to make sure that we're getting what we're after. So basically, in this case now, if I come back, this joint here controls the alignment. This one, because it's been drawn not the best, these two, this now controls, and this joint now just follows that position. So it's still locked in place, but we've been able to fudge past this poorly drawn model. Granted, if we were to take this to the boss or anything like that, you could literally say, due to the fact of it being so poorly represented in the geometry in the card, I've had to put that in there to allow it to just align it correctly, so I can still get a result. So we're going to get a result, but it's just in case if somebody questions you as to, well, why is that there? That is why it's there. What I'm going to do, because I'm going to obviously save this, I'm going to upload it, and you can all take a look at it. But I'm just putting that there because of just for your notes, really. Right. So we've now got that free body to move. The next thing that we have on here is we have where the spring damper sits. Now, technically, we have a joint to represent that. Really, the question is, could I not just, let me hide that out. Could I not just use that as a representation? That's the real question. Do you even need it? That's the point. So what I'll do is I'm going to bring in, a point. So what I mean is, if I just come back to this, oh, I didn't want to do that. I'll just bring this back. Now we know, based on that model, we know that it's actually middle of here, that the fixture for the spring damper sits. Now I measured this between here, between each end cap, if you will, is 80 millimeters. So what I'm going to do is go back, and I'm going to go RID, whoops, RIG, get this right in the end. Oh, what am I doing? What am I doing? Swear to God, starting off so well. Right, alright. So I'm going to go rigid transform. Bring in the rigid transform. I'm going to revolve that. Close that. Revolve that. And based on where that was sitting, I'm just going to stick it just at the back end of this revolute. And what I'm going to do, oh, 1 second, visitor arrives. What I'm going to do now is I'm going to create the point of where that'll be fixed. Just as a reminder for anybody who's arrived, my big fix is the cylindrical joint. I can still have the revolute behaviour, it can move along the shaft to take into consideration for misalignment, but this is the main control. So we're still getting the result. Anyway, back to the point. So I'm going to do a midpoint between, so I'm going to double click in. And what I want to do now is, I know that the millimeters in between each point is actually 80 millimeters. So I'll go Z, and I'm going to write this in this way because I want you to be aware of where this dimension is coming from. It's just in case you do open this up and go, where did that dimension come from? If I go 80/2 and you measure it, you'll go, oh yeah, that's where it came from. So that's why I'm doing it. So if I click apply and then OK. Right, so we know that we want the spring damper to behave in this axis. Don't forget, everything by default is in the Z axis. So this being rigid transform 1, what I'll do is extend it, and I'm just going to update my diagram. So we've got rigid transform 1. Base comes from the world, follower sits in the middle, which is exactly what we'd said. Which is exactly what we'd said. Right, sorry, I was just allowing people on the Adobe Connect. So we'd said that is now bang in the middle. Now, with any axis, with any sort of behaviours, we need to take into consideration that this Z needs to be in this particular position. Z is essentially needing to be where X is. Now, this is a rigid transform reference, so I'm going to come back, I'm going to go into my rigid transform. This is where rigid transforms are really in their own. They really do exactly what you need them to. So I'm going to go to Y, I'm going to go here, I'm going to rotate my Y 90 degrees, and then what I will do is apply, then run it again. I need to update the diagram because I don't need to see it swinging. I know it doesn't run right yet. So I'm going to run it again, come back, and now we've got this running. If I go rigid transform, we know that we've got this central point. Z is in that key area where we want it to be. All we need to do now is start to look at bringing in a spring damper joint. So I'm just going to drop that. And then what I'm going to do is go to my library. So under forces, spring and damper force, I'm going to bring that back, bring that in. Connect it up. It's going to get messy as this, so I'm just going to bring that up here and just drag it down a little bit, just to give me a bit of space. I can bring that across and then rotate it. Oh, gotta have a tidy box. Right, so that now puts it into position. I'm going to configure my spring damper. Now, when I measured it between each point, it gave me a free length of around 92.79. If you were going to add this on, what you could do is do the housings of where the joints sit and then connect them there as well. In the assignment, I'm not going to scrutinise too much if you've chosen different ways of doing it. This is what I'm trying to promote. I'm trying to promote you just having a real ponder at these things and really thinking about these things, because this assignment is far from easy, as you should now really notice. So I'm on to natural length, and I'm going to add a spring stiffness. Now my spring stiffness, I'm going to go in relatively strong, so I'm going to go 240 Newton meters, which, given the size and the weights of everything that I'm running, it won't be too bad. So what I'll do is I'm going to go with a tenth of that. So I'm going to go at 24 newtons per meter per second, and now this is going to give me some type of response. Then we can really start to look at this even more, and that's the key thing with this. We need to look at this as much as possible. 2 seconds. Right, so what we essentially need to do is we need to create the point of where the lower arm interfaces with. So if I come to my lower arm, and if you remember, we were using just the left side as key points, or else if you go left and right, it becomes very tricky and a little bit frustrating. So what I've done is if I measure between here and here, it's 5 millimeters. So what I'll do is I'm going to connect a connector here, then do a rigid transform to here, and then we're ready to go. And then we've literally got everything completed, and we can start getting some results and having a look at what we're getting. So I'll come in, I'm going to add a new frame. We'll call this, I don't know, spring damper. and I'm going to go by reference of geometry, spin it round. You remember we're coming down this side, only on this side, and I'm going to go, I'll probably go here, like that. So we've got Z moving downwards, and we know our axis sits there for the minute. We are going to have to twist it in a minute, but we're going to use the rigid transform to allow us to do that. So I'm going to hit save, hit apply, just check, everything's in position, and that's sweet. So I'm going to come back out of there, and I'm just going to bring that down a bit, and bring that down. It's just, I joke about tidy boxes, but it's a good way for presentation. And when you're really presenting it, it really gives you an idea to everything that you're doing. It just looks good, you know. So what we knew is that we were moving down Z, because if you remember, Z is moving down where that connection point is. I'm going to bring this one down. I'm just going to borrow that. I'm going to need to modify this anyway. So it needs to know where it'll sit. I'm going to connect you to there, and I'm going to connect you to there. Now, from here, I'm going to do a rotation along Y again, because if I just quickly open up this, if I open up that, and then I show these key points, see there that our Y is actually here, moving upwards. If I do 90 degrees, that'll push it to where X is. So I'm going to do the same thing here. I'm going to rotate it 90 degrees, and along Z, I'm definitely not moving that. Along Z, I'm moving positive, and I'm going to go 5 millimeters, because remember the distance in between each point was 10. So if I hit OK, that now allows us to run it. We've not got any results yet, and we will get results, but I just want to test it and find out. So I'm going to run it. Okay, that's great. Now with this, it's going to have some constant force acting on it, and then we're going to hit it. We're going to do a bump in the road. That's what I'm going to recommend with this. So first things first, I want to start extracting some values to give me some ideas. And with this, of course, I'm wanting to tune to try and get my critical damping. So I'm going to double click in, and where I think my critical damping sits, I'm actually going to be able to verify this through any different types of equations that you want to use. But a common one for this, funnily enough, is Euler, and using Euler's second order system equations. Runge cutter tends to be a little bit better. Some get very frustrated with runge cutter though, but runge cutter tends to be a little bit better. Right, the other thing I want to do is I want to sense this position as well. I'm going to sense the hub, and that will let me know the type of response that we're getting as well. It don't have to be the hub. We could sense it from a joint. We could sense it from anywhere. I'll use the head though, because it's clear that when it moved then that there was some oscillations that occurred. So what I'll do now is I'm going to go into my library, and I'm going to go, in fact I'm going to snap this to the left, snap it to the right, spacebar, swear to God, love spacebar. Right, now what I'll do is I'm going to go down to frames, transforms. We're going to go transform sensor, and just like we did on the bar linkage, couldn't even think of the term there, on the bar linkage system, just like we did on there, what we're going to do here is sense the end of it. Now there's no end connector on there yet, so what I'd like to do is I'm just going to add one on. So I'm just going to go on my connector, and there doesn't have to be a connector there, by the way, but I prefer one to be there. So I'm just going to go call it wheel. And then I'm going to go base, select on here. I can go there. If I use that as a selection, I know that my key element here is probably going to be the X component. That's going to give me the biggest performance of what's going on. So that's just something to keep in mind, because that's what we're going to test for, if you will. So what I'll do with that is I'll tab it on, pull it down a little bit, tab it on, pull it down a little bit, and then as like before, I'm going to use a world frame to give me a nice solid reference. Bring that down, connect it in, and what I will now do is I'm just going to take some translation. If I do translation, I'm going to go translation around the X component. This will just give me position, and that position will show any types of oscillations that we're getting. So from there I'll go. Now don't forget, with this we've got this triangle like structure. So if I go to utilities, I'm going to go power string to Simulink converter. Now as a reminder, the critical damping, if I do, in fact if I go half critical damping, 1 second, half critical. So that is the effective damping regime. Now I was referring to here, half. So it's, as they nickname, a bump and a bit. What we're going to do is try and tune this to give us them results. Then once we've got that type, we want to try, well, your idea then is to really want to try and verify exactly what you're getting. So I'm going to tab that in. And then I'm going to go back to my forces, because my force is over here. Bring that down and tab another one in. This is the one thing where they could really do with getting right, because yeah, I still don't quite like that. You got to always use these. If there was a nice magic way to bring them all out, like a mu or a demu, just to essentially have one and then just keep them growing out, or have multiple outputs. Anyway, right, rant over. I'm going to drag and drop a scope. Go 2. Bring that into there, bring that into there, and then scope it out. I could probably bring that back a bit, it's a bit clumsy. Right, so as it runs, let's see it running. So this is it just free falling. So this is just over the top, it's just free falling. It's like when you pick a car up and the wheels will maintain themselves off the ground, if you will. So this is not ideal, so we do need to add a few bits onto it. Not convinced with it. However, that's a good start. You can't see which one you're looking at, so I'm going to break these into 2 and then zoom it again. I mean, to be fair, that's actually not so bad. That's not so bad at all. The way that it's responding is not so bad. I wouldn't be confident that that would give me something ideal yet, just because it looks about right. It's a good start, but there's no real force hitting back on it. There's no real response giving it back. If you remember on the example of the bar linkage, we'd loaded it. Now, on the assignment for, I'm not going to use the same values for the assignment, by the way. That's why I've been making these numbers up, because I'm not using the same values for the assignment. So what I've done, what we want to do is we essentially want it to be responding under a level of weight. So basically it's sat somewhere. And then what we want to do is we want to initialize a hit to cause it to displace, and that would give us a bump in the road, and then we'd be able to naturally pick up on what we were getting. So what I'm going to do then is I'm going to go to my library browser, scroll down, I'm going to go to forces, and I'm going to bring in my external force and torque, bring that in, spin it round, come on you swine, spin it round, and connect it up for the minute. Just leave it there for a second. Hit save, because we're now starting to build a level of where if anything goes wrong, this will massively go wrong. So it's saying here what force component are you operating in. I'm going to actually move because I know that I'm checking the displacement of X, so that's the right component I'm in. So that means I'm going to actually apply a force in X. Click apply, and then we end up with the Simulink to power stream conversion. You can see it there, the triangle. Whoops. You can see it there, the triangle. That triangle confirms it's looking for something like that. So what I'll do is drop out, go to my library, and go to utilities, and I'm going to bring in Simulink to power stream converter. Bring that in. Now I'm only going to load this with a light amount. I mean, like I said, I did test this, so I'm only going to load this with a light amount, and because it's only little. Then what I'll do is come back, and we could put a constant in. Constant value will just hit it solid. It's not really going to give us anything. Not really. Arguably, if you wanted to do a road simulation, if I go to sources, you've got random number generator. That is one particular way that you could do a bumpy road. The trouble is there's no real measure to it. So when you run it, you come away and go, I'm not 100% convinced. So personally, for me, I prefer applying steps. Now, I actually don't use the step itself. I normally use the signal builder, because we can design it, we can manipulate it, and we can choose how it's going to interface. So let's bring that back across, bring that down, and then connect. I'll just bring that up a little bit. Oops, oops, oops. Bring that up a little. Oh, it's not working well for me at all. Doing so well. Oh, I'm going to leave it. Oh, there we go. Now what I want to do is I'm going to literally create this. So from my signal builder, it comes in as a step. So this is over 10 seconds. I can choose multiple steps. I can do as many signals as I want onto it. One initial step I think is going to be good enough. And if we choose, let's see, we're over 10 seconds. If we have a 2-second period of where this is initialized, so it's a big ass bump, or we can shorten that. But it's nice to keep it separate, because any types of activity we're looking for is the response of the system. It is not the overall, so it's just the response. So what we'll be looking for is around this area, and also around this area. So what I'm going to do is send this in at, we go Y, and with my Y, I'm going to go -2, purely because I'm hitting it with a force moving against that axis that we'd put onto it. As really, if it was operating from the main one, it would be slightly differently, if you will. Because the component, you've just got to move with the alternate component. So I'm going to go -2. And then from my upper value, I'll then drop to I'll go -8. So 2 to 8 newtons. Want to just make sure that's in there, so double click in. And obviously, as ever, it's an input as a single signal, single input. So I'm going to go Newton, confirms a Newton, click apply, and then we are ready to test. So I'm going to bring up my scope again, and then I'm just going to take a look. So I'm going to hit run. Force is out, as you'd imagine. Force goes high on the initial response, settles itself out when it's balancing up to its own weight, and then returns in a similar sort of offset here. And you notice for the position, we've got an initial similar position here. The only thing I don't like, and I'm sure some of you have already noted this, one thing I don't really like is if you look at, so if let's just shrink that down, and then let's just bring that right across. We need to tidy this signal up, but look at the sharpness of this. This is the relevant tolerance. But you look there, that is still noise that's going, it's still settling. It's technically not what we're after. So if it's still settling, arguably, are we not looking at something more like, let's have a look, 0.25. This is where verification comes in quite useful, because you kind of look and go, it looks right, but is it what we're after? So if I go back again, I'm going to tidy that signal up because it's a bit messy. So I'm going to come in and I'm going to offer some more resolution for it. I may even go as brave as to go double of that relative resolution. And then if I run again, let's take a look at what we're getting. That is more what I'm after. See what I mean? So if I move to here, then what I will do is I will just trim between here and here. I mean, no, saying that, look at that. Arguably, it's actually pretty good. But again, you'd have to really pull out to find out what that zeta is. But it does seem to cut off. So we've ended up with a bump, and it does seem to cut off. I would probably suggest that the damping on that is too strong. So if we just tune that a little bit more, 2 seconds. If we tune that a little bit more, and what I'll say is I'm going to bring that down quite a factor, drop it to 18. Oops, 18. Now if we run that, I'm going to go run. See if that gives us something better. Larger overshoot. We'd end up with a more impact here. So you can see there that obviously with dampers, all they essentially do is they will hold the energy. They will disperse the energy, as springs will hold them and give us. They will contain the energy. Damper will dissipate the energy, and by lowering that ability to dissipate the energy, we get a lot more of an aggressive response. So you can see that there on the initial bump. So I'm just going to check the wheel itself. Is it giving me something like I would imagine? So if this was travelling along a road, if I hit go, so it's travelling, you can see here it's being supported, then it gets hit, and then drops back down again. And you can almost see that elastication response of what we're looking at. Yeah, so I am glad I was able to draw a line underneath that. These types of responses are what you would typically get in any type of ideal scenario testing. I chose, now looking at it, I chose not the best example to do it because it was a poorly made model, but I like to think that I was able to also offer a solution of what happens if it's a poorly made model. How do you actually solve it? Because not all models will be perfect for what we want to do. That one, I'm pleased that we're able to do that. Well, yeah, I mean, to be fair, to be fair, basically, it genuinely did catch me off guard. If 2 seconds. If you look at it at first, I looked at it and thought, oh yeah, that's a nice little example that we could work through. And then when after yesterday, when we'd gone through it and realised it was such a crap example, I just could have died. I really could. I'm not gonna save that, because who would save that? So yeah, that is in essence a way to solve it. So yeah, I've luckily been able to recover a little bit because of somebody poorly making it. This one's the ultimate way of fixing it. I am not finishing now, but what I'm going to do is I'd like to stop this recording and then start the next recording, because what I also wanted to do today was a gearbox. And in true Blue Peter fashion, I have worked through this morning myself to make sure it's going to work, to make sure it's not going to fall on its arse, and to make sure that the model by the way is actually pretty good, to make sure that the model is something we can genuinely use. So yeah, I wanted to go through that because I know there's a few people who are doing the gearbox, and this gearbox, it puzzled me a bit this morning, but I'm going to try and take you through some of these puzzling bits that I hit this morning. So give me 2 seconds. I'm just going to stop this recording on here. What? Yeah, I'll stop this recording on here because I like it just to be a finishing off of that example. So I'll stop that recording.